In this worked example, we're going to be looking at dynamics. Question 1A1, define acceleration. Class, what did you say for that? Everybody said it together, well done. The rate of change of velocity. The rate of change of velocity is the habit you want to get into for defining things in physics that are rates of change. So acceleration is the change in velocity over the change in time. That's the same as the rate of change of velocity. Okay, it's better to write it out in words like this than to leave it, as an equation. If you write the equation, then you need to sort of say where A is acceleration, B is velocity, and T is time, and make sure you sort of explain everything, define each variable. State Newton's first law of motion. An object maintains its current state of motion unless it's acted upon by a resultant force. Resultant is a good word to sort of keep in mind for, well, when do things not sort of maintain their current state of motion? When resultant or net forces, sometimes it's worded as a net force, but I would say as an AICE Physics student, get in the habit of defining it as a resultant force. Because remember, when we do vector addition, we always say, if we add two vectors, the sum is the resultant. So if there is a non-zero, force acting on it, a resultant force, it's going to accelerate in that direction. Yesterday, we looked at some examples with equilibrium, and you may recall the closed vector triangles. There's no resultant, right? Like it all just closes up and it adds to zero. And so in that situation, you just have constant velocity, and zero is a special constant velocity. So sometimes it's worded like this. An object at rest remains at rest, an object in motion remains in motion in a straight line, okay? And the reason why we have to sort of qualify it like that, if you say an object maintains its current state of motion with constant velocity, because velocity is a vector, all you have to do is change direction to accelerate. You don't necessarily have to change your speed, right? Like you can move at constant speed and round a curve and you'd be accelerating, okay? And objects don't do that. Objects don't move in circles on their own in this universe of ours. Forces are required to move things in circles. Okay, it's called a centripetal force. So let's try to, put that down in a nice, concise fashion on these two lines right here. So I would say an object maintains its current state of motion. And you could, kind of open up parentheses and say, if it's at rest, it will remain at rest. If it's moving at constant velocity, it will remain at constant velocity. Velocity is a good word because it's a vector. And so that sort of captures the idea that if you change direction, right, velocity being a vector where direction matters, then you are changing your velocity. And what do we know about a change in velocity? That's acceleration. So even changing your direction is an acceleration, right? An object maintains its current state of motion until or unless a resultant force acts upon it. All right, and that would get you the mark there. So the Dr. Schleif way of thinking about the first law is sort of in a negative sense. Objects don't accelerate on their own. I like to kind of think about it like that. Objects aren't just going to accelerate on their own. They're just going to keep on moving at constant velocity. And a special constant velocity is zero. Like things at rest just remain at rest. If something was at rest and it all of a sudden started moving, you wouldn't say, oh, the laws of physics are different than I've experienced my whole life. You would be looking for an outside force. You'd say, what caused that to move? Was there like a gust of wind? Was there a magnet, like a magician does a floating trick or something like that? And you're not like, oh, wow, this person doesn't live in the same universe as we do with physics. It's, they've got different laws of physics. No, you'd say there's some outside force they're exerting on that object that it's, they're it's just not apparent, right? So 2 marks for those. We've talked about sort of being proficient in getting the low-hanging fruit, definitions, statements of the laws, make sure that you're taking your time between now and the end of the year to use whatever learning strategy you've hopefully found for yourself throughout your academic career that works for you. Flashcards, journaling, study groups are great. If you guys aren't already, meeting up at the library every weekend, for 8 to 12 hours, a day on Saturday and Sunday, then you should probably start doing that, right?
The library is closed on Sunday.
Well, don't let that stop you. You guys know physics, okay? You know physics. And I'm joking. You should probably spend 15 hours a day. I'm just joking about the 8 to 12. Now, in all seriousness, try to have a study group, people that you can discuss the physics with. Talking your way through it is very helpful. Okay, so, and that tends to be towards the end of the year. Students are more mindful of that. It's never too early to start reviewing your physics, especially when it's AICE Physics. All right, so this graph then goes the variation with time t of vertical speed v of a parachutist falling from an aircraft is shown in figure 1.1. So take a moment to study that. And let's just sort of, give it the once over here. We haven't read the question yet, but let's just sort of interpret this velocity time graph, almost like it's a learning objective that we want to sort of master here. There's two things we can do with graphical analysis. We can take the area underneath the curve, or we could take the slope. Okay. What is the slope of a velocity time graph? It gives acceleration, right? So we define acceleration, it's the rate of change of velocity. So here we see a change in velocity as a rise, and we see a change in time as a run, right? So when you do rise over run for slope, you're getting velocity over time. The units you're getting are meters per second, or meters per second squared, which are indeed units of acceleration. Okay, so you can see all that. So it starts out at a velocity of 0 at rest, but then it increases its speed. Okay, so there's acceleration there, right? The slope of this would give the acceleration. It almost looks like, it's hard to see the scale on there. Maybe you can on YouTube, but I'm recording this on Zoom and there's like a little sort of toolbar there. So if this is 10 seconds, then like 1 second would be like maybe about here. And it looks like about 10 meters per second. So .4, 0.8, so 1 second would be about here. It looks like it's not quite 10, maybe it's something like 9.8 or something like that. So I don't know, 9.8 meters per second squared. Okay, this is probably Earth, right? So we can kind of see that the slope of this gives the acceleration due to gravity. So like after about 3 seconds, look, it's picked up about 30 meters per second of velocity, but then something happens right here. How can we interpret this? What's happening to the slope right here? It's getting less steep. So if the slope is velocity, and we have a changing slope, we have a changing velocity, right? I'm sorry. The slope gives acceleration. And if we have a changing slope, then we have a changing acceleration, right? It's not accelerating as much anymore. Okay, so here it's like constant acceleration. It's just accelerating constantly. This is a pretty straight line. As the line starts to curve, that's no longer constant acceleration. Okay, eventually we just level off and we achieve this sort of top speed. It looks like it's about 50 meters per second. Okay, so the acceleration goes from, that due to gravity, about 10 meters per second squared, but then it's not accelerating uniformly anymore. It's still picking up speed, but the rate that it's picking up speed is decreasing until eventually it's just at a final speed. Okay, what is the slope of this part of the graph right here between B and C? Can anybody, find some points and do a calculation, or does anybody can just look at that and go, you know what? Here's the slope. What's the slope of this part of the graph right here between B and C? Good job, everybody, 0. So you just have to stay null, it's just nothing. So we'll just stay silent, right? Can everybody appreciate that this is a flat line right here that has a slope of 0? So remember, the slope of velocity time gives acceleration. There's no more acceleration here, right? It's leveled off. It's like I'm done accelerating. I'm at my top speed, my final speed, my terminal velocity. Okay, so this is terminal velocity. Why do we reach terminal velocity? We're going to go back to Newton's first law of motion that we just talked about. We're going to sort of anchor our thoughts on that. Okay, objects maintain their current state of motion until an outside force acts upon them. When a parachutist jumps out of an airplane, there is no longer a normal force underneath their feet provided by the atoms that the airplane is made of, right? They willingly, let that normal force just sort of stay behind, right? They take a step out into the air, which has a lot of space between those molecules, and so they start to fall. So when you're in an airplane, like at time negative back here, you've got weight acting down, but you've got a normal force keeping you in the airplane. As soon as the person steps out of that, airplane, no longer can the atoms provide that normal force, but they still have weight, right? And so what you're observing here is an acceleration due to gravity. So you have weight and weight alone acting down from like A to about right about here. Once you've picked up, 30 meters per second, 35 meters per second of velocity after just a few seconds of falling, you're going to be crashing into a lot of that air. All right, and that air is going to exert a force called drag force. The drag force is proportional to velocity, and at really fast speeds, it's proportional to velocity squared. Okay, so sometimes it's proportional to just velocity. Sometimes the drag force is proportional to velocity squared. But in any case, it's, there's some proportionality between how fast you're going. It should make sense because you're crashing into more and more air, right? And so it's exerting a greater and greater force. And so by about here, you still have the constant weight vector down, but now you're getting a more pronounced drag force. By here, you're going faster still, your weight stays the same, but now the drag force is stronger yet. And by this time, what can we say about the drag force? It's equal to your weight, because if the acceleration is zero, by virtue of the fact that the slope of this is zero, yesterday, remember talking about if A is zero, then what can we say about the net force, the resultant force? It also must be zero, even though the parachutist has mass. 0 times whatever that mass is a zero resultant force. And so you reach terminal velocity when the drag force equals weight. You won't speed up anymore, because now the drag force is counteracting what was, you're still falling down, right? Really fast. You're falling down at 50 meters per second. So don't interpret this as like displacement, right? This is showing what your speed is doing, your velocity. Your velocity levels off to this final top speed. What do you think causes this decrease in velocity then? What happens at point C for here's the clue, the parachutist. Yeah, parachutist, right? It's not a skydiver, it's a parachutist. They deploy a parachute at sea. What does a parachute do? Just like the drag force is proportional to velocity, one of the other factors governing drag force is like the cross-sectional area of the thing falling, the density of the air. Like there are equations that we can calculate what the drag force is based on, like I said, density of the air, cross-sectional area of the thing falling, other factors. So the point of a parachute is that it's a lot of surface area. And so at sea, now you have a net force this way. The drag force is much more pronounced than the weight. So if you're sort of, trying to keep the weight vector constant, right? The person isn't gaining or losing weight throughout this motion, but the up vector is changing from nothing to a drag force that's bigger and bigger until it's equal to weight. And then it becomes much bigger than weight when you deploy a parachute. Which way is the net force now once you deploy a parachute? The up is winning that fight, right? It's like the up is a greater magnitude than the weight at that point, which means you're going to slow down. You're still falling down. Okay, so like the positive direction is down. You're going with, positive velocity. It's still positive, but it's decreasing because the net force is acting against your motion. Okay, so now you're going to slow down. The only way to slow down is when the net force acts against motion. Okay, just think about that with a little bit of common sense. If you want to slow something down, you got to push it against the way it's moving. If you push something with the way it's moving, it always speeds up. You can never slow it down. Like, you push a bowling ball in the way it's moving, it goes faster that way. There's no way to slow it down. You gotta push it against it. And so here it's going to slow down, but remember that that drag force is proportional to velocity, right? And so once again, it's going to level off and it's going to sort of become equal again, but at a much safer landing speed. Okay, so here is another sort of no more acceleration. The acceleration is back to 0. The weight and the drag force are equal because this thing is, again, proportional to velocity. So as the velocity decreases, the drag force decreases also. It's crashing into less air, right? And so the drag force is, all over the place, right? It's 0, it's stronger, it's equal to weight, it's bigger than weight, goes back down, it's equal to weight again. So drag force is tough because, right, it's an artifact of like all of the air molecules that, object is crashing into and relates to cross-sectional area and other things. But we can look at this velocity time graph and think about the slope gives acceleration. What's the acceleration doing? And then we can anchor our thoughts onto Newton's second law of motion and really say, well, what are the forces doing? This is a more simple problem because we're only considering two forces. We're considering weight down and drag force up. Remember, one of the statements at the beginning of this graph was about the vertical velocity, right? We're only looking at the vertical velocity, right? This isn't the wingsuit problem from yesterday where the guy was like flying at an angle 24 degrees and covering a bunch of ground. All right, so now that we've kind of really interpreted this, I think pretty thoroughly, we should be able to answer any question about it and maybe do some calculations. So let's see what that's going to look like here. First thing, it says calculate the distance traveled by the parachutist in the first 3 seconds of the motion. So we had mentioned that. We spent a lot of time talking about the slope or the gradient, but we did say first, like there's 2 things you can do with graphs, right? And one of them is find the area underneath the curve. And so the area underneath the curve gives displacement. Again, we can always use the units as a clue. If it's an area problem, in this case, it's going to be a triangle, right? So we're going to have 1/2 length times width, or 1/2 base times height. And so we're multiplying velocity times time, right? Like the velocity is going to be like the height, the time is going to be the base. So 1/2 base times height. Let's just use that familiar sort of equation for a area of a triangle. And you said if this was 10 right here, then each of these is 0.4. So it's 0.4, 0.8, 1.2, 1.6, 2, 2.4, 2.8, 3.2. So 3 would be like in between these 2 lines. Here, I guess. Three 3.2, 3.6, 4, 4.4, 4.8, 5.2, 5.6, 6, 6.4, 6.8, 7.2, 7.6, 8, 8.4, 8.8, 9.2, 9.6, 10. All right, well done. So right here, we can see that it neatly crosses at, now what's the scale on this? I think it just goes up by 1, right? 21, 22, 23, 24, 25, 26, 27, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Yeah, if you count it carefully, it is indeed each square is 1. So that's 29 meters per second. Okay, right here at 3 seconds, right? So we know this, the base is 3 seconds. We know the height is 29. So 1/2, 29 meters per second times 3 seconds. I had to rewrite that. I already had it right there. And then seconds are going to cancel. This is what we were talking about yesterday with using base units as a sanity check on your calculation. If you're solving for distance, then the product of your terms should give you units of distance, right? And they do. Meters per second times seconds is meters. So we've got distance or displacement equals velocity times time, right? We're kind of using this equation. And so what is 1/2 times 29 times 3? Yep, that's exactly what I had in my calculator long before you all did. 43.5. 44 meters. That's what I would have put down. Did anybody put down 44, or did you guys put down 43.5? Probably 43.5 would earn both marks, but be mindful of significance because you can lose marks for being too precise. If you're within like one significant digit, you usually earn the mark. But if you're, if we're 43.5859, and you write all of that out, then it probably would cost you a mark, right? So be mindful of the significance. 2 significant digits here, 2 significant digits here. 44 meters of distance traveled in 3 seconds. You jump out of an airplane, gravity accelerates you 44 meters underneath the plane, 3 seconds after you jump out. Explain the variation of the resultant force acting on the parachutist from point A at time t equals 0 to point C t equals 15 seconds. Remember, point C is when the parachute is deployed. And so these 3 marks are explaining just what we did with our force vectors. And so I'm not going to write it all out in words. I'd like you all to kind of do that for yourself, but think back to what we just discussed, or if you're following along at home later, just rewind the video and go through that, until it's sort of making a lot of sense. And so at time t equals 0, remember there's just the weight vector. So it's like t equals 0, only weight, because you haven't picked up any speed. So there's no air that you're crashing into exerting any drag force initially at t equals 0. So the resultant force is just down due to weight. Okay. But then as time goes on, and here it'll be easier for me to actually, let me redo this just slightly. All right, that's your weight, 2 lines. Okay, so it's always going to be that. Lines down. So the length of this vector here is showing the constant weight of the parachutist. Initially at time t equals 0, that's all you got. But then as you pick up speed, you get a little bit more drag force. And so what's the resultant? Well, how do you add vectors? Put them head to tail, draw a line from, the tail of the first vector to the head of the last vector, right? And so it's basically like, well, this is stealing away a little bit from this. And so it's not all the way down, but it still is a net force acting down. So you're still accelerating, right? But just not as much. And then, so the drag force is just getting bigger and bigger until it's eventually also 2 lines, okay? And so that's when we got to point B. I forget what time point B was, but I remember between B and C, that's when we had the flat sort of part of it. And so if that's 2 lines down, that's about 2 lines up, or it's exactly 2 lines up, we can all tell that. So here we've got the force due to drag equal to the weight. And remember that weight equals mg. And that's just for sort of bonus learning as we go along. Like, it's good to remind ourselves of all the useful equations. So at this point, and this is point B, okay, we still have to say, well, from B all the way until 15 seconds, the resultant force is 0, right? So from here over, the resultant force is 0. YouTube, you can still see what I'm doing, but in class, for whatever reason, my projecting screen just kind of disconnected here. So my apologies for that. Students that are live right now, people watching this video hundreds of years in the future are like, oh, that would have been so cool to be in Dr. Slice's class. You just get to watch the videos on YouTube now, centuries later. How easy go. All right, we're back. So from point B all the way to point C, you just have a resultant force of 0, right? The resultant force is 0 because the drag force equals weight. Right, so resultant force is 0 from B to C. The resultant is just the weight initially, and then it's still down, but it's a little bit less down still, until eventually it's 0. So like this vector right here in tasteful pink ink is the resultant. Actually, that's red for resultant. You guys see it, right? So the resultant is not as big as the weight, right? Because we're subtracting this drag force from the weight, right? So the resultant is not as strong as it was initially. That's why the curve starts to level off, right? Until eventually it's 0 when they become equal. Again, we're taking all the time in the world that we need to try to make sense of this physics with this problem study. If you're sitting for paper 2, you're not going to spend 46 minutes working on, 3 marks. You're going to kind of know the physics by then, say, oh, okay, here's the key idea. These are the vectors, kind of put it in your own words, but make sure you're always answering the question or, reading the directions carefully. Explain the variation in the resultant force. So the resultant force becomes less and less until it is 0 from points B to C. Right? The resultant force starts out equal to weight. Right? The weight is the resultant force because there's no other force besides weight at time 0. But then the resultant decreases because the drag force opposes weight. Right? So you have to subtract them. So some statement like that in your own words, but make sure that you're using the language of the question. Like if you don't say resultant force in your answer, you're probably not going to earn the marks. So you're explaining the variation of the resultant force. Okay. The resultant force, I would use that to sort of like, what do they say? Turn the prompt around. Turn the prompt around, TTPA. There's some acronym. It's like, I don't know. It's like an elementary school thing where they teach, writing, and like turn the prompt around, and just kind of like explain the variation of the resultant force. The resultant force, acting on the parachutist is, and you kind of use that to help sort of design your sentence there. Jamming on the language. So that's a 3-mark question, and sometimes those are really tough marks to earn because students will say things that's kind of like it sounds physicsy, but it's technically incorrect. And so you got to be just careful with your language. This is why on the very first day we talk about precise definitions, knowing what a resultant force is. Remember, I mentioned in your statement of Newton's first law, use that resultant, right? Because that's kind of the way that AICE is going to kind of talk about, not a net force, a resultant force, right? When you're adding vectors. Here we're only adding 2, right? And they oppose each other. So it's kind of simple. No Pythagorean theorem, right? We don't got to have anything at some angle with a sine function. It's just, okay, drag opposes it, so we subtract it. It gets less and less until it's 0. Now it says, describe the changes to the frictional force on the parachutist at t equals 15 seconds, so at point C. The frictional force is drag. So like drag is friction with air. Okay, like you're crashing into air. So the frictional force is the drag force. All right, so at point C, it's 1 mark. What is the change to the frictional force? So we could sort of keep the same thing going. So if our weight was initially 2 lines down, and then at right before point C, it was 2 lines up due to drag, then at t equals 15 point C, that's where we go like that. Right? That's when the drag force becomes greater than weight. So your statement here should be something about this. The frictional force, the drag force, is greater than weight at t equals 15. You don't have to say anything about a parachute probably, but you probably could, and that would make sense, right? Like you can infer that that's the point when the parachute was deployed. I don't know if there's any other way to explain that. Well, yeah, there might be actually, but let's just stick with the parachute. All right, so the changes to the frictional force. Well, the frictional force has been changing the whole time, right? Getting bigger and bigger. So the resultant force has been going down and down. But now the frictional force, the drag force, becomes much more pronounced, much greater in magnitude than the weight. And that's why there's a net force up. If there's a net force up and you're falling down, you're going to slow down. And that's where we see, like at point C, remember, that's where you see sort of the graph goes like this, right? That's when it sort of drops sort of very, very sharply like that. And then it says what's going on between t equals 15 point C and t equals 22 point E. So at t equals 15 point C and t equals 22 point E, we have the same kind of physics going on here, but just sort of slowing down. So, right, so there's a constant slope right here due to the drag force from the parachute, but then because drag is proportional to velocity, as we slow down, now this thing is getting shallower, shallower. And so once again, at point E, the drag force becomes equal to weight again, evidenced by the zero slope from E onwards. So what's happening here is the same thing that we just sort of mentioned, right? That drag is proportional to velocity. So as you slow down, you're crashing into less and less air. The drag force gets lower and lower and lower until eventually at point E, it's once again equal to weight. But thankfully for the parachutist, it's at a much safer landing speed, right? Here you haven't deployed the parachute. You have a certain cross-sectional area as a parachutist, as a skydiver, let's say, without a parachute being deployed, right? It's just in your backpack right now. And this is why, like, there's like sky surfing and things like that. They used to be like on the X Games. I don't know if they still do that anymore on X Games. It's just like skateboarding stuff. We used to have sky surfing, and like depending on how the aerial acrobat positions their body, they're either going to sort of be diving down very fast, or they can sort of splay their body out, so they're increasing their surface area, right? And so they're sort of in control of velocity in that regard, doing like a nose dive, so head first sort of down, or if they're sort of have more surface area. So there's some amount of control there. But the parachute just has a lot more surface area than the human did, right? So that's why we sort of see this happen. So once again, try to put that in your own words. Or what question is this? 1B 3 2. Right, this is just question. I love the way multiple part questions. This is question 1B 3 2. 1B 3 2. We're just doing one question today in AICE Physics, right? And we've just made it to part 1B 3 2. Moving right along. That surely got to be the end of this. Oh no, there's more. The mass of the parachutist is 95 kilograms. Calculate. Oh, I love that verb. One of my favorite verbs, you guys. I like it better than explain. Explain. Calculate. Okay, we can calculate. Calculate for the parachutist between t equals 15 seconds, point C, and t equals 17 seconds, point D, the average acceleration. All right. So you all that are live in class, everybody in the future is sort of envious of you. You could probably find some points to do that calculation, in front of you. We know that it's the slope, right? So you just got to find some points there. And really, if you can, so there's a certain velocity at 15 seconds. And so that's going to be the initial velocity. There's a certain velocity at 17 seconds, v minus u over t2 minus t1, right? So like acceleration, change in velocity over change in time. We defined it way back when. V minus u over t, but if the initial time is 0, or if the time corresponding to the initial velocity is 0, we usually just see it like this, but sometimes it's helpful to see it like this. T2 minus T1, like the initial velocity at time 1, the final velocity at time 2. And since they give us those times, anytime they give you a question like that, they sort of gave you your denominator for you, right? So kind of use that. Now, if it's a constant slope there, which I think it is, you're not really restricted to those times, because there might be other points that are sort of within that are easier to sort of read off. And if it's a constant slope, it shouldn't matter which points you use. All right, so you kind of got this set up over here. Let me clean up this part of it a little bit. So it'd go, if that's 18.6, 18.2, this would be 17 point, oh, wait, 19.6. 19.2, 18.8, 18.4, 18, 17.6, 17.2. So look, it's an even 20. They were friendly. And then it was between this one right here. So it's like the final velocity is 20, the initial velocity is 50, right? So it's slowed down, right? So it's negative. And then corresponding to 17 minus 15. Is this the calculation that everybody has out there? Or does anybody do a different calculation besides that? Did anybody find different points within that to do this with? So it's going to be negative 15 meters per second squared then, right? Negative 30 over 2 or negative 15 meters per second squared. Note that that's steeper down than this is rising. This is due to gravity, right? Weight is force due to gravity, right? Your weight is the force due to gravity. And so we know that the acceleration due to gravity is 9.8, and we see that that's paired out with the data. Here, it's a sharper drop, right? So this is like with more than 1 G force, you're slowing down. 1 G force is what you're feeling right now, 9.8 meters per second squared. Question?
I did the equation wrong, but I still got the right answer.
How did you do it wrong?
I did 15 minus 20 over 15 minus 7, but I still got the right answer.
You did 50 minus 20 over 17 minus 15.
Oh, sorry, I got 15 minus 20 over 15 minus 7.
So yeah, my advice would be, yeah, mathematically it works out the same, but you want to sort of focus on which was final, which was initial. Okay. So we're slowing down, right? Point C is at 15 seconds. That's initially how fast we're going to 17 seconds, right? Where the final is. And so you'll tend to avoid mistakes. It may not have, hurt you here, but it could in the future. The average frictional force, I think maybe that's like something we'll save for another day. How could we calculate that? Oh, wait, we can do it immediately. 15 times 95. That will give us the net force, but we also have weight acting down. So the average frictional force, this is when the parachute is deployed, are solving how big is it. MA gives us the net force. Okay, so we're summing these two forces. We've got weight minus the frictional force, which we know is drag, and that's going to be equal to 95 times 15. All right, because we know that mass times acceleration gives the net force. Those are our bells here. Remember, weight is mass times G, 9.81. So we solve for weight, we solve for the right side, we solve for the drag, and you can do that on your own YouTube. We'll see you next time. I got astronomy coming in.